Cool. And just like that, we have this big, terrible picture of a whole bunch of green dots that you probably were not expecting to see as you jumped into the next video, or maybe you looked into the notes and you saw this was going to be coming. But the goal of this last kind of little video is to chat a little bit about just kind of some of these detectors of, is this collection of numbers that we're actually working with like suitably random? Is it actually something you would expect, or is it doing something else entirely? So there's a bunch of different tests for kind of this suitable nature of randomness. The one that we're going to look at here is going to be this Monte Carlo value for pi. It's a cute one, so it's one that I like to bring up. There's obviously going to be tests about looking into the entropy or the averages or all sorts of other things as well. Each one of those tests are going to be great on their own. Each one are also going to have flaws, is that you can create a collection of numbers that pass one of these tests but are still not, random enough, things like that. So the idea behind this Monte Carlo value for pi test is that we're going to try to come up with an approximation for pi. So this nice mathematical constant, which again is this utterly crazy process, but it works really well and it's just fun to implement as well. So in front of you, you should hopefully see this kind of big square that has a bunch of green dots in it. And hopefully those green dots look suitably randomly dispersed through this region, but we don't know for sure. So the way that we're going to try to identify if they're good enough is we're going to try to see if those dots can somehow be used to approximate this value of pi. The way that this is going to be connected is that we're going to use a couple nice geometry formulas that we know the answers to. And when we compare them together, it's going to simply extract out this number of pi, so we can start to get things that are going to be balanced out fairly nicely. So the way this is going to go down is that we know the area of that little circle. So formally, the picture I drew has kind of a radii value of 1, but here, think about the radius as being an r. That will typically be like the modulus that we have in play, or, the total, size of the x values that we're working with, because they can range, between 0 up to something. Or maybe we normalize it and we center it at 0, so it goes between, negative something up to positive something. So the picture is drawn with a 1, but think about the r as being a general r. What we can do is we can very easily compute the area of that circle. So flashback to a little bit of high school geometry or middle school geometry, or whenever you figure out the area of a circle as being pi r squared. So r is that constant we're going to have from our system, and pi being the mathematical constant. Likewise, it's really easy to compute the area of that square. So the area of that square is just length times width. Well, if you look at that square, that's going to be connected to the diameter of that circle, which is 2r. So the area of that little square is going to be d times d, or 2r times 2r, or more naturally referred to as 4r squared. Once you have that, you can start taking fractions of things. So the area of the circle divided by the area of the square to compute that fractional amount of space. So the circle is inside of the square. So that number, kind of what we should see, is going to be the area of the circle, so pi r squared, divided by the area of the square, so 4r squared. The r squareds kill each other off, leaving you with a pi over 4, which tells you that pi, as that constant, is then going to be equal to 4 times the area of the circle divided by the area of the square. So you get this nice connection between some objects that we can kind of manage, and then this constant on the left. So when it connects back into some of our, simulations or some of these random data points that we're going to work with, is that we don't really have this idea of an area of that circle, but I can count the number of dots that are in that circle. Likewise, I can count the number of dots that are in the overall square, and think about those as essentially being my area. So my pi should then somehow be close to being 4 times the number of dots in the circle divided by the total number of dots. Basically, if everything is as it's supposed to be, that number should kick out something like a pi. If all of our numbers end up being in this range, so they'd all be in the circle, and none of them would be outside of the circle, when you took that ratio of dots in the circle divided by total dots, that's just going to be a 1. So then that formula over here would just kick out 4 times 1, which is 4, which is not a good approximation to pi. Likewise, if you had all of your dots, out here, and none of them were in the circle, well, then that ratio would then be points in the circle, which is 0, divided by points in the square, which would be all of them, which would still then give you this ratio of 0. So you get 4 times 0, which is 0, which is not a good approximation to pi. So those are kind of your bounds on this, is that this expression over here is going to kick out some number between 0 and 4. We're hoping that it kicks out some number very close to pi, basically showing that things are in the balance that they are supposed to be. It's not a perfect test because you could still have, a correct distribution. Maybe all of the points on the inside are all in that little blob. And this part right here is completely empty, which would not be a good random situation, but it's, one that would pass this test. So it's, again, not the only test you should use, but it's one that's fun to use, fun to look at. It's got this kind of nice, weird math connection of things, which I'm obviously going to enjoy looking into. So I'm going to swap over to the code. We're going to run this process on our linear congruence one that we had before, and then I'll also do it on that hashing one that we just looked at in the last video as well. So I'm going to swap over to things. I have some of it already preset just so we can hopefully not have to rerun them all, but I got the green bar, so things look okay. Over on the right, you'll hopefully see a scatter plot of some things. So here I'm going to have to pull in some packages to do some of the plotting for us. What I'm going to have in this first run is this linear congruence one. So what I'm doing is I'm going to create a bunch of X values. They're going to have a specific seed. They'll have their own multiplier. They'll have their own increment. I'm going to create a bunch of Y values with the same seed, but slightly different multipliers and increments. The one thing that they will have in common is that they'll have the same modulus. So what that will look like on the backside is I'm going to get a whole bunch of essentially ordered pairs. So think about the left list as all of my X's. My Y's are all going to be in this list. I have them in binary if you want to look fancy as well. So then those are going to be all these points that are going to be plotted up on this little image up above. So then the question becomes are those dots suitably random, or do they have some funky things going on? Are there too many of them in the circle or too many of them outside of the circle? When it came to plotting, I did a little twist. So the numbers that we generated were all going to be between 0 and 255 because I have my little n as being an 8. So the number of bits is an 8. So my modulus is going to be 256. That would create numbers up in the top right quadrant. So my circle wouldn't be centered at 0, which is not something I wanted to deal with. So rather than move the circle, what I've done is I've taken all of those points and I've basically subtracted off 256 divided by 2. So that all of the numbers, instead of being from 0 up to 256, they're between negative 128 and positive 128. So you have that as your R value. So it's the same dots that we had here, except for think about all of those numbers as having essentially your modulus divided by 2 subtracted from it. So that creates your little bin. So then this little test, so when we're generating those numbers, we're going to ask, do those points live in the circle or do they not live in the circle? So here we're going to use our old school kind of what is the equation for a circle. So like x squared plus y squared equals some r squared. So I'm going to ask, is x squared plus y squared less than or equal to my r squared? So here's that shift. So you have the x, but then moved over. And then your r then becomes not the n, but it becomes n over 2. So if you're inside of the circle, then the number of circle points goes up by 1. So it's initialized as being a 0, and then it goes up by a 1. Run it through the rest of the way. I got a couple other printout things that are going to emerge at the end. So the first thing is I'm going to compute the average of all of the x values. That gives you a test of kind of how random are they. Likewise, I'm going to have an average for the y values. I'll print out the number of points that exist inside of the circle. And then I'm going to have this bit of arithmetic to try to approximate what pi is. The closer that thing is to pi, the better this is going to be situated as. A scatter plot to actually show what's going on, which is that over there on the right. So if I hover over all of these things, oh no, it's got some crazy double printing. All right, we're gonna have to hit stop and rerun, so hopefully it goes quickly. Actually see the, okay. So what emerged on the backside is that I have this thing generating some number of points. So if I go back into my code, the number of points that I had it generate was going to be that 256, but then I divided it by 4. So I didn't need to have all of the points regenerated. Because if I go over 256, I know that I'm going to start having repetitions. So I'm only looking at a subset of them. So of that, you can see that my X bin of things, These are going to be those numbers that are shifted by 128, has an average of about negative 11.5. If they're all shifted by the same number, so they're balanced, that average should be fairly close to 0. So what that's saying is that these numbers are all shifted down a little bit more than they should have been, where the y numbers are actually pretty good. So they all were about what they should have been. But it also then shows that, my pi approximation is about 3, which is not a great approximation of pi. It's not terrible, but it's not the best approximation of pi that anybody's ever seen. So some things that you can do, you could obviously change up some of your seeds. You can change up the number of points you generate. There's all sorts of things that you can actually start to do. So let's try to up the ante a little bit by going up to 10. So the number of bits that we're going to work with is going to now be a 10. What that will do is that will change my modulus. So it's no longer going to be a 2 to the 8th. It's now a 2 to the 10th. And let's see if this just blows up when I actually try to draw this. Probably will. So I may end up having to kill this thing, but we'll give it a go. All right, so that actual one's too bad. The other ones are going to be much worse. So here you have this collection of dots that are going to reemerge again. I have the same seeds, same other things, except for my modulus is different. And you can see that just by having slightly larger numbers and also more of them, I'm getting a better approximation to pi. Still not great, but it's getting better. A couple of things that I have here that I am mentioning that we should probably maybe try running is trying things out with things that might not have as good of stats. So if I go back to this 8, so these two numbers that we started with, so these seeds of 1 and 13 and 37, those were some of the ones that we saw before. So if I go back to my linear congruence page, so if I change my seed to a 1, and if I have this as 13 and this as 37, so if I run that, this one with a modulus of 256 actually has a full cycle length. I'm going to run through all 256 numbers, which then when we come back to this thing, if I'm only grabbing the first, fourth of those, I'm not going to have any repeats, which is nice. If I were to actually start running things with things that maybe cycle too quickly, so if I change this to an 11 and change this to a 7, I go by my little notes. My cycle for that is going to be a 64. So if I look over here, you'll hopefully see something that looks much less random because they're hitting those numbers way too quickly. So if I have a cycle of 64, it's not so terrible. It's terrible for me to try to move around and stuff like that. But make that nice, make this nice. I got too many things going on with my page. So what's happening there is that you're actually going to start seeing a little bit of repetition. If you start looking at some of the dots, you can actually start to see some things that are going to look the same. It's a little bit more obvious once we start changing some other things to have really bad data points. So if I change this to a 10 and a 10, and if I were to try to run that, you'll see a lot of these y values don't change hardly at all. The x's do a little bit of change, but the y ones don't. So if I'm struggling with this. All right, so if I were to scroll through that little list, hopefully you can see it on the bottom. They're all basically, once they get up to the number of 198, they're then stuck at that number of 198 forever. So in your picture, you have something similar like that emerging. Unfortunately, if you look at this little pi test, it actually still does a pretty good job of saying that it's random, because if you were to draw that circle around that thing, you would still have the correct number of points inside of the circle as you would have outside of the circle. So again, it's not an end-all be-all test, is that there are some systems that may end up cheesing it a little bit that will end up, passing the test to a certain level, but obviously not looking very random at all. There are other ones with this linear structure that will still pass it, but it will look very, very predictable. So here I changed my AY to be a 77 and my CY to be 143. So if you look in, whoa, maybe not. All right, let's try to run that with a slightly larger collection of things. Go. If you start changing some of those stat points up, you can start to see this kind of linear shape, which is still kind of problematic, is that it's got these slices that are going to emerge. It's got a pretty good, pi test, or not terrible pi test, but it's going to have a little bit too, consistent on the values on the inside. So you'll see in your activity for Friday, I'm going to give you some of these to play around with a little bit. So I'll feed in some numbers for you to poke around to kind of explore some of those. Basically, it's changing up some of these things, seeing the output emerge on the backside. So on D2L, I do have a link for it with this linear congruence, but I also have it for some of these hashing ones as well. Basically, once you have the process for plotting those things and looking into it, then it's easy to change it up to whatever process you want to. So if I run it with one of these ones that I seeded with the hello world or, password for my Ys, it'll look really similar. Should look really similar. It's all slow and bad right now, so maybe I'll let this think, and then I'll hit pause in the video because I've been talking a while anyways, and you're probably ready to start working on the activity anyways. So the activity will poke into this stuff a little bit more to kind of run this pi test, as well as seeing some that are good runs, some that are going to then be bad runs for things that are way too consistent or not consistent enough. So it's basically a lot of just changing up some of those numbers to some interesting things to see the dots that are in the circle versus the dots that are not in the circle. So anyway, I'll pause it there just because I'm rambling now and you don't want to hear it. You just want to get to work. So I'll let you go and do that. So if you got any questions, as always, let me know. Have fun.